What's up, everyone? In this video, we are going to learn about discrete random variables. Yay! It's actually a really easy topic, and I hope at the end it makes a lot of sense. All right, so before we talk about a discrete random variable, I guess we should talk about what a random variable is. So a random variable is a numerical description of the outcome of a chance event. So basically, a random variable is a variable that takes on the possible numerical outcomes of a chance process. Okay. I know that may seem a little bit confusing right now, but we've already learned about a chance event or a chance process, right? Anything where we don't know the outcome. If the outcomes are numerical, boom, that's a random variable. So like when you toss a coin, the outcomes are head or tail. Those are words. That's not numerical, so that's not a random variable. But if you roll a die, the outcomes are 1, 2, 3, 4, 5, 6. That is a random variable because the outcomes are numerical. So any situation, any chance event where the outcomes are numerical, that is what we call a random variable. Now, we oftentimes use a capital letter X to represent the random variable, kind of like a variable, right? So, if I let D be the outcomes of rolling a die, there are multiple outcomes, a 1, a 2, a 3, a 4, a 5, or 6, but D is the letter I'm using to represent what could possibly happen, but they have to be numerical outcomes. So moving forward, when we talk about random variables, got to be numerical outcomes. All right, so there are two types of random variables. We're really going to focus on discrete random variables in this video, but I do want to introduce you to the second type, which is called a continuous random variable. So a discrete random variable, this is a random variable that can take on a countable or listable set of outcomes. So the outcomes, it's possible to make a list of the outcomes. Think of it as that, right? You can make a probability chart where you have all of the outcomes listed and all of the probabilities associated with them next to it. So example, let D be the value of a die once rolled. That would be discrete because I could list every single outcome. Here I go, 1, 2, 3, 4, 5, 6. Very simple. Where a continuous random variable, this is a random variable. Hope you guys are okay with me using RV for random variable. It's just a lot easier to type. But this is where there's an unlistable amount of outcomes, okay? So there's basically infinite amount of outcomes. I couldn't possibly make a list. I couldn't possibly find all the probabilities. For example, let S be the amount of seconds Jimmy takes a shower. Yes, every time you take a shower, that is a random variable. You don't know the outcome. Could be 32 seconds, could be 34 seconds, could be 35 seconds, could be 117 seconds. I mean, it could be 1,000 seconds. I don't know how long Jimmy's going to take a shower. The list of possibilities is seemingly endless. And then even if you throw decimals, like I guess it could be, 67.2 seconds or 149.3 seconds or 792.6 seconds. Now that list becomes even more continuous or endless. So that's a continuous random variable. All right, here's a couple more examples. So Vin plays a video game where the score is a whole number ranging from 1 to 85. So that would be a pretty long list, but I could certainly list G, the random variable, the outcome of a single game, anywhere from 1 to 85. That would be discrete, even though it's still a long list. It's not endless. Kelly tosses 2 die. Oh my gosh, 2 die. And S is the sum of the 2 die. The sum can be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. That's a listable set of outcomes. Doug shoots 10 arrows at a target. Let B be the number of arrows that hit the target. Well, he's only shooting 10 arrows, so none of them can hit the target. 1, 2, 3, 4, 5, 6, 7, 8, 9, or all 10 of them can hit the target. That would be a discrete random variable. Again, the outcomes are numbers that I can make a list for. Continuous would be, okay, we're going to measure an elephant in pounds and let E be the weight of a randomly selected elephant. Oh my gosh. Baby elephants all the way to huge elephants. I mean, especially if you start measuring the pounds in decimals, boy, oh boy, there could be an endless amount of options for the weight of an elephant. Now, you might say, well, no, all elephants weigh between 700 pounds and 1,200 pounds. Okay, but even in that interval, it's still a pretty endless list, especially when you include decimals. Speed is measured in miles per hour for a car. Let S be the average speed of a NASCAR race car during a race. So, there's 40-some cars in a NASCAR race, and what is the average speed of any randomly chosen car? I don't know, 200.2 miles an hour or 198.7 miles an hour. I mean, the list is seemingly endless. So those would be examples of continuous. Now, a probability distribution, we've actually already kind of talked about this, but a probability distribution is any representation of the possible outcomes and the associated probabilities. So again, we love probability distributions because they tell us everything we need to know. They tell us all the outcomes and they tell us all the associated probabilities. So let's be honest, you could really only make a probability distribution with a discrete random variable because you have to be able to make a list of all the outcomes. They're kind of hard to do if it's continuous, but we're actually going to try in another video when we make a video for continuous random variables. This one is going to try to focus on discrete. Now, this probability distribution could come in the form of a table, a graph, or a function. All right, so let's kind of make sure we talk about all these. But remember, anytime we look at a graph, we should probably talk about the shape, center, and spread, right? This is numerical data, and numerical data has a shape, has a center, has a spread. So we're going to make sure we comment on that when we look at some examples. Now, anytime you're working with numerical values, we could find things like the median, the mean, the standard deviation, the IQR. We could find all of these things because, well, we've already learned about how to look at numbers and analyze numbers. So again, all we're doing is looking at outcomes and analyzing some information about those outcomes, which we should be already pretty good with as long as they're numbers. So let's talk about the median, for example. You guys already know this. The median has 50% of values above it and 50% of outcomes below it. So a median value has to have 50% of outcomes above it, 50% of outcomes below it. I mean, it's really that simple. All right, so let's look at our first official example here. All right, so we're going to let the random variable Q be the number of employees who work at a certain restaurant on a given day. Now, there's only 5 possibilities. 20 employees, 21, 22, 23, 24. That's it. There could be no more. There could be no less. This is discrete. I literally just made a list of everything that can happen. And then next to each outcome is the probability. For example, there's a 10% chance that 20 people are working, 10% chance that 21 people are working, 10% chance that 22 people are working, 40% chance 23 people are working, which is the most likely, and again, 30% chance 24 people. All those probabilities have to add up to 1 or something is really, really wrong. Because again, I'm literally telling you that this is everything that can happen. So is this discrete or continuous? Well, we kind of already mentioned that. It's definitely going to be discrete because I just made a list of it all. You can make a list, it's discrete. What is the shape of the distribution? Well, check this out, right? This is actually pretty easy to do and think about, right? We could make a list down here, 20, 21, 22, 23, 24. And think about that. 20 is 10%. 21 is 10%. Oh boy, I'm doing a really bad job at making this. I gotta refix this. Sorry about that. So 20 is 10%, 21 is 10%, 22 is 10%, 23 is 40%, and then 24 is 30%. Now, I know I don't have a beautiful y-axis here for these, but again, now we see, oh yeah, that's skewed left. Why is that skewed left? Because the outcomes to the right, the larger numbers, 23 and 24, are much more likely than anything to the left side. Okay, it makes a lot of sense, right? All right, what's the center? In other words, what is the most typical number of employees? Well, if you're skewed, we learned way back a couple weeks ago that you prefer to use the median. So what value has 50% above it and 50% below it? Now, technically, we say at or below and at and above because discrete, you can actually be a specific number. So we don't just want 50% below, it's 50% at or below, 50% at and above. So the only number that works for is 23. So that's going to be my median. Now, if you don't see why, let me explain why. Well, because the median has 50% at or below. If you add all those up, you get actually more than 50%. That's fine. It just has to be at least 50%. And it also has 50% at or above. It's actually more than 50%. But again, that's the idea of a median when it comes to a probability distribution. There has to be 50% or more below, 50% at or above as well. Okay? So that should make a lot of sense. No other number will meet that qualification. So for example, if you thought 21 met that qualification, no, 21 only has 20% at or below. It has enough above, but not enough below. So there's only going to be one number that will have the 50% or more above and below. That's how you find the median. All right, what is the probability that there are at least 22 employees on any given day? So we're trying to find the probability that Q, the number of employees at work, is at least 22. At least means greater than or equal to 22. Well, that would mean 22 employees, 23 employees, or 24 employees. So we'd simply add those probabilities together. They are mutually exclusive. You can't have 22 and 23 people working at the same time. So we're totally fine to just add away here. So we're going to do 0.1 for the 22, or 0.4 for 23, or 0.3 for 24. Add those together, we get 0.80. So it's an 80% chance that at least 22 employees are working on any given day. All right, let's do another example here. So at a school fundraising event, there's a raffle. Let P be the random variable for how much you could win in the raffle. So the raffle is either going to cause you to win $1, $5, $10, $20, or $50. These are the only 5 outcomes, which makes this definitely discrete because I literally just listed everything that can happen. The associated probabilities are also listed very, very simply. What's the shape? Well, hopefully everybody's thinking skewed right. The outcomes of 1 and 5 are much, much more likely. 1 is way up here at 60%. 5 is at 30%. And then 10, 20, and 50 are very, very low. Very, very low. $50 only a 1% chance. So we definitely have a skewed right distribution. All right, now what's the center? Well, once again, we're trying to find that median that has 50% at or above it, 50% at or below it. Well, the only number that that's going to work for is right here, $5. There's actually a lot above, so at or above, so that's going to be 30, 5, 4, and 1. That's 40%. Oh, wait a minute, maybe I'm wrong here. Yeah, that's not actually going to be the median because that doesn't have enough, right? I thought it was. I was mistaken. There's definitely enough below. There's actually 90% at 5 or below, but there's only 40% at 5 and above. So that's not the median. Sorry about that. I made a mistake. Oh my gosh. So the median's actually $1. Who would have thought that the median is all the way at the bottom? That's because $1 is just so much more likely than everything else. So again, there is more than 50% at $1 or less, obviously, and there's 50% at $1 or more. So that would be the center, $1. And again, that's because it's just so much more likely. All right, what is the probability you win at least $5? So the probability that the amount of money P that you win is greater than or equal to $5. So again, greater than or equal to 5 would be $5, $10, $20, or $30. Oh, excuse me, $50. Add all those together. That's going to be 0.30 plus 0.05 plus 0.04 plus 0.01. That's going to be 40% chance. Now, the opposite of that would be you don't win at least $5, which another way I could have gotten 40% is to simply say, well, the only outcome that I'm not happy with is $1. That's 60%. So that means there's a 40% chance that I win $5 or more. But again, adding them up is very, very simple to do. All right, here's another one. Let the random variable S represent the age of the attendees at a local concert. And we're measuring your age and the number, the whole number that you currently are. That does make this discrete. So I'm going to say, how old are you? I'm 38. How old are you? I'm 35. You can't be a decimal amount. It's a whole number only. And I asked as many people as I could, and literally this is what I came up with. There was nobody older than 40, nobody younger than 32. Crazy, but that's just the way it was. All right, so that definitely makes it discrete because, again, I literally have a list. Now, instead of just giving you the probabilities like I did with the previous two tables, we just have a histogram here, and the height shows you the probability. So, for example, 38 is about 25% of the attendees were 38. 35 looks to be right around 10%. You get the idea. Got to do a little bit of estimating here when you have a histogram. What's the shape? I hope everybody's saying skewed left. The outcomes on the right are much more likely than the outcomes on the left. What is the center? Once again, we're looking for that 50% mark. Where's their 50% at or above, 50% at or below? Well, looks like my guess is going to be 38 because we got 25, we got 20% here. That's already 45%. And then it looks like we got about, I don't know, looks maybe about 8%, a little bit shy of 10. So definitely more than 50% at 38 and above. And then what about at and below? So once again, 37% looks maybe around, right around 15%. 36 looks to be maybe around 11%, just trying to eyeball it. Again, I'm not perfect here. 34 looks to be right around 5%. 33 maybe 4%. 32, maybe 2%. So there's definitely 50% or more at 38 and below. So that's how you find the definition of the median there. So the median would be 38 years old. All right, what is the probability that a randomly selected attendee is 37 or 40? So we're trying to find the probability that S equals 37 or 40. Now, those are mutually exclusive. You cannot be 37 and 40 at the same time. So basically, all we have to do is add. So the probability that your 37-year-old is about 15%, give or take. Probability you're 40 years old is, again, about 8%, give or take. Add this together. There's a 23% chance that a randomly selected person is 37 or 40. Pretty easy. All right, so the only other way a probability distribution can be represented is with a function. We showed you a histogram, which is a graph. We showed you a table, nice and simple. So how can a function do this? Well, this can only be done in special situations, and here's one of them. Let M be the random variable for how many free throws J can make out of 8. Now, that is a discrete random variable because out of 8 free throws, he can make, I can literally make a list right now, he can make 0, 1, 2, 3, 4, 5, 6, 7, or all 8. Can't make a negative amount, can't make 9, he's only shooting 8. Can't make a decimal amount, so that is discrete because I can make a list of everything that can happen when Jay shoots 8 free throws. Now, if we know that he's an 85% free throw shooter, which means on any given shot, he could shoot 85%. The point I'm trying to make here is imagine a function where I say, well, what's the probability that Jay makes 5 out of 8? Okay, a function, right? You guys know functions, inputs, outputs. I plug 5 into the function, and out comes the probability that he makes 5 shots. This type of function does exist. I know, mind-blowing, right? Just wait a couple days, we're going to learn it. This would be called a probability distribution function. You put in the outcome, it gives you the probability. Now let's just quickly go back to this table real quick right here. This table is acting like a function. What's the probability that you earn $20? 4%. But, it was just a table that gave me the answer. It wasn't a function, it gave me the answer. Kind of like an input-output table, right? Input, $20. Output, hey, 4% chance. So again, imagine a function that does it all for you. It's not a table that you look at. It's a function, a mathematical function. You plug in 5, it spits out the probability that you make 5 out of 8 shots, or Jay makes 5 out of 8 shots. I'm going to teach it to you, but not right now. Just give me some time. All right, now, the big thing that we want to talk about is the mean and standard deviation. Anytime you're working with numerical-based outcomes, you can find a mean and you can find a standard deviation. Now, in a couple examples we've seen so far, we were kind of like, finding the median, which is great. I hope I explained that good enough. Might need to go over a little bit more in class, but it's not too bad. But you can also find the mean and the standard deviation. A little bit trickier, though. But before I teach you how to find the mean and standard deviation, you really got to make sure you understand what the mean is. The mean of a random variable is the average of many, 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 many trials of that chance event. The standard deviation would be how much an outcome could vary from that mean. Okay, so once again, this is actually the law of large numbers. The true mean of a random variable will only reveal itself after a large number of trials. All right, so one example I've typically done in the past to kind of help kids understand this is how many points LeBron James scores in a basketball game is technically a random variable. It's unknown. I don't know how many points he's going to score in tonight's game. It is a number, so it's numerical. That definitely makes it a random variable. And I guess it would be discrete, right? Because if you think about it, you can't score negative, so I could start at 0. He can't score a decimal amount in a single game. And, I guess you could say, well, he could score 1,000 points. Yeah, that'd be pretty much impossible. So there's got to be like a set list, like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and, he has scored, I don't know if he scored 80 points in a game or not, but, at some point, it might be a long list, but we could make a list. Okay, so here's my point. If LeBron James played 5 basketball games, and he scored 20, 25, 27, 28, and 36 points, I could find the mean of those 5 games. Pretty simple. Add them together, divide by 5. Easy, right? But what's the true mean? What's LeBron James's true average? What is his true mean? Well, to do that, I wouldn't just look at 5 games. I would look at many, 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 many games. In fact, I would look at every single game he's played. And that would be the true mean, mu, of all of his games. And, LeBron's, a rookie who's only played a couple games, his average is kind of bouncing around a little bit because he's only played a couple games, where LeBron has played literally thousands of NBA games. So he probably does have a pretty consistent career average based on many, many, many games. And that's the mean we're talking about. All right. So the mean of a random variable is the average value of that random variable if it were to repeat it a large number of times. So if you think about a random variable and you were to repeat it over and over and over again, the mean would be the average outcome of those many repetitions. Now, it's also known as the expected value. Think about why this makes sense. The mean of any variable is simply what we would expect that variable to be. So like LeBron's mean is how many points we expect him to score on any given night. So if LeBron's career average is 27.2 points, and that's an average of many, many, many games. If you say, how many points is he going to score tonight? Well, I guess I would expect him to score 27.2. But guess what? It could vary. He might score a little more. He might score a little less. So that's why a mean always comes with a standard deviation. Pretty simple, right? And LeBron is so good, I would actually expect his standard deviation to be pretty low because he usually scores what he averages. And there's very rarely that he ever goes super low or super high. He's pretty consistent. Okay, where other NBA players are very inconsistent. They might score 0 points. They might score 40 points. They're going to have a large standard deviation. But I really want you to make sure you understand what a mean of an expected value is. All right, so let's go back to this example where we're looking at Q, the number of employees that work at a certain restaurant on a given day. So again, on any one given day, there's 5 outcomes. Let's just say on day 1, there's 22 people at work. Okay, well, that's just one day. But imagine we were to repeat this random variable many, 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 many days, right? And again, imagine if we were to do this. Oh, go to the restaurant. How many people working? Write it down. Next day, how many people working? Next day, how many people working? Next day, how many people? Just over and over and over again. Now listen, what's going to happen is most days there will be 23 people working. Why? Because that's most common. 23 or 24, probably what's going to happen the most. But there will occasionally be a day with 20, 21, 22 people working. So again, the mean of many, many, many days would be the mean number of employees that we would expect to see over a large number of days. That would be the mean, the expected value. How many employees would you expect to see over a large number of days? So law of large numbers helps us understand probability, but it also helps us understand the mean of a random variable. Now, how do you find the mean? Because it's not just adding up these 5 values and dividing by 5. No. That wouldn't be fair because the 23 is worth more. The 24 is worth more. They should be valued more because they're more common. So here is how you find the mean of a random variable. It's actually the really easy formula. Now, this is the mathematical statistical formula. Don't let it confuse you. It's very, very simple. First, notice the symbol we're going to use here. We'll use mu because this is a true mean thought over many, 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 many trials. And we put the variable that we're talking about as a little subscript to kind of personalize it. Now, how do you do this? It's very simple. You take each outcome multiplied by its probability, and then you add them all together. It's that easy. Outcome times probability. That way, when we multiply, we're going to take 23 times 0.4. Giving it more weight. 21, 20, and 22 only get multiplied by 0.1, giving them less weight because they don't happen as often. It's that simple. It's the easiest form in the world. Don't let this math thing confuse you, right? Remember, this sigma here just represents adding them all together. So we take every outcome, times it by its probability, add all of those multiplications together. It's that simple. Just make sure you always use the proper symbol, which is right here. And I'm going to actually teach a little shortcut to do the work for you. But anyway, the most important thing is that you know how to explain what a mean is. It's what we would expect after a large number of trials of the random variable. All right, so the mean is very simple to do. Most kids actually do it by hand. It's literally just outcome times probability plus outcome times probability plus outcome times probability. Very easy. But what about the standard deviation? A little bit uglier. Here is the formula for the standard deviation. Much uglier formula. And I'm just going to be honest to you. I am never, ever, ever going to expect you to use this. I want you to make sure you know the notation. Sigma is the formula for the standard deviation. And X, again, is the random variable. Kind of personalize it there. Now, don't worry about using this formula. Seriously, you never will use it. I'm going to teach you how to get your calculator to find that standard deviation for you. In fact, let's talk about it. Let's go back to this problem right here with the employees. How do we find the mean and standard deviation? Well, it's very simple to find the mean. You take each outcome times its probability. Standard deviation, not so much. So here is all of my math work. I kind of took my time doing it. But again, the mean of Q is the number of employees. So this is the average number of employees on any given day. So I took 20 times 0.1, 21 times 0.1, 20, this should be a 22. Typo alert, sorry about that. Plus 23 times 0.4, plus 24 times 0.3, and I got 22.7 employees. So in the long run, after many days, I would expect 22.7 employees to be working. Now, please understand this, just like LeBron James. He might average 27.2 points a game, but that's literally impossible for him to do. It's an average, right? It's what we expect, but we know it's not going to happen because he can't score 27.2 points. Same thing here. You can never have 22.7 employees. It's an average. It's a mean of many days. It's just an average. And notice how it favors, right? It's closer to 23 because, again, 23, 24 are much more likely. Now, the standard deviation formula is there, but again, don't ever worry about having to do that work by hand. Trust me, we're going to let our calculator do it for us. But the standard deviation is 1.27 employees. So what does this mean? This means on any given day, if I look at this restaurant, and before I go in and ask, I would expect 22.7 employees to be working there, on average. But that number could easily deviate by 1.27 employees. So if we were to examine a large number of days, the mean number of employees per day would be 22.7 employees, and on average, the number of employees per day could vary by 1.27 from the mean. Now, how do we get that answer on our calculator? All right, I would actually encourage you to get out your calculator, do this with me, but I'm going to teach it to you right now. First, you're going to hit Stat, Edit. Stat, and then Edit. And in list 1, you're going to type in all the outcomes, 20, 21, 22, 23, 24. Next to them, in list 2, you're going to type the probabilities. Make sure they correspond. They have to line up just like the table. That's pretty easy. Quit, exit out of there once you get that in. Then you're going to go Stat, slide over to Calc, and select one variable stats. You're going to use the lists in 1. List 1, that's where you enter the outcomes. So list 1 should be the outcomes. But we have to take into account the frequencies, or the rate at which these outcomes occur. And that's list 2, because we have to take into account the fact that, for example, 23 and 24 employees is much more likely. So remember, when we did this back a while ago, we left the frequency list blank, but now we're taking into account probabilities, so we have to put that probability list in list 2 for frequency list. Hit calculate, and the very first number at the very top is the mean, 22.7. Now, the only thing I hate is that they use X bar. I've actually written several letters to TI asking them not to use that, but they do anyway. They haven't responded to my emails. So it's not X bar, it's mu. Because remember, this is a mean of many days. So even though we didn't look at many days, that's what the formula represents. And then they did get the standard deviation right. That's sigma 1.27 is what I said it was when I did the math. I guess I should have rounded to 3 decimals. But anyway, that's sigma, that's the standard deviation. They did get that symbol right. It's literally that easy. I mean, how simple can that get? All right, now, I do want to mention that we call these numbers parameters. The mean and the standard deviation of a random variable are known as parameters. Remember, parameters come from populations. And the idea is, like if you think about it, right, random variable Q is the number of employees at a restaurant on any given day. Well, the population would be all days, every day. And that's technically what the mean and standard deviation represent. Because remember, that's what we're trying to tell you. The mean is the average in the long run, not after 10 days or 100 days, but many days. And it's pretty cool that we could calculate that without actually looking at many days. So they do not come from a sample. It's not like I said, let's just look at 10 days. That would be an X bar and an S. Those would be statistics. This is a theoretical idea of the mean and the standard deviation that we would see after a large number, infinite maybe, of trials. okay, which we could look at as the population. So they both must be interpreted using correct units and context to be very specific where they're coming from. Let's look at another example so you can practice this. All right, this is back to our prize money. So at a school raffle, we could win $1, $5, $10, $20, or $50. Everybody's a winner, so something's going to happen. You could hopefully win $50, but most of the time you're probably just going to win the one. All right, so what is the mean and the standard deviation of P? Well, listen, your calculator could do both, so don't even waste your time doing it by hand. I mean, seriously, I know finding the mean by hand is pretty easy, but your calculator could do it. So right now, in list 1 of your calculator, enter the prize amounts, 1, 5, 10, 20, 50. In list 2, enter the probabilities, 0.6, 0.3, 0.05, 0.04, 0.01. Double check that you typed them in right. You don't want to make a silly mistake. Then you're going to go stat, slide over to calc, one variable stats. List 1 is your list. That's where you typed in the prize amounts. If you did it in a different list, well, then you obviously need to adjust. List 2 are the probabilities. That's the frequency list. All right, so make sure you type that for the frequency list. Hit enter, and you should get an average prize amount, the very, very top, I know it says X bar, of $3.9. And the standard deviation is $6.24. So what does this mean in context? If I were to enter this raffle, not once, not 10 times, not 100 times, but many, 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 many times, over the long run, I would expect to win an average of $3.90. So let's just say I played it. I'm going to get a lot of $1. I'm going to get occasionally a $5. And every now and then, maybe a 10, a 20, and very rarely a $50. But in the long run, if I play this game an infinite amount of times, the average winnings would be $3.90. But, of course, it could be higher. Obviously, look at the numbers. But it could also be lower. And that's where the standard deviation comes into play. So, on average, the amount I win could vary by $6.24. Pretty easy. Let the calculator do the hard work for you. You just got to worry about interpreting. All right, let's look at another example here. We actually saw an example like this in class a while ago, but let's go over it because it's a pretty cool problem that we could do mean and standard deviation with. All right, a horse race plans to race in 2 races. The probability he wins the first race is 30%. If he wins, that's conditional. If he wins the first race, probability he wins the second is 45%. If he loses the first race, the probability he wins the second race is 10%. Create a probability distribution for W, the number of wins. Okay, so how many wins could this horse have? Well, I guess he's running in 2 races. He could have 2 wins. Well, he could have only 1 win, or he could lose them both and have 0 wins. But to make a probability distribution, I need to find the probabilities of each of those outcomes. So let's make that tree diagram. So the probability he wins the first race is 30%, which automatically tells me the complement, 70% chance he loses. Now, here's the conditional. If he wins the first race, there is a 45% chance he wins the second. Complement rule, 55%, he loses the second. If he loses the first race, the probability he wins the second race is 10%. And that would be, complement rule, 90% chance he loses the second. So 2 wins, where there's only one way you could have 2 wins, and that would be 30% times 45%. So 2 wins would be 30%, 0.3, times 0.45. Sorry for my messiness there. 0.3 times 0.45 is 0.135. So that's the probability of 2 wins. 0 wins would be 2 losses in a row. Well, there's only one way that can happen. 0.7 times 0.9. Just multiplying because he's got to lose and then lose again. So that'd be 0.63. That's actually going to happen quite often. And then 1 win. Now, this is where we got to be careful because there's 2 branches that lead to 1 win. He could win and lose. So that'd be 0.30. I'll use parentheses here. Times 0.55. Or another way he could have 1 win is lose and then win. So that'd be 0.70 times 0.10. So I got to figure that out here. Let's see here. 0.3 times 0.55 plus 0.7 times 0.1 is 0.235. And one way to kind of check your work is to make sure that all those probabilities add up to 1. If they don't, you did something wrong. All right, so find and interpret the mean and standard deviation. So if he were to, again, the scenario is he runs 2 races. How many wins can he get? Imagine this horse does 2 races. We record how many wins he has. Does 2 races. We record how many wins he has. Does 2 races. We record how many wins he has. And we do this over and over and over and over and over again, right? So the mean would be how many wins we expect him to get in the long run. So that is the mean of W. All right, so once again, we're going to go to our calculator. In list 1, we're going to type the outcomes of 2, 1, and 0. In list 2, we're going to type in the probabilities, 0.135 for 2 wins, 0.235 for 1 win, and 0.63 for no wins. Then we're going to go stat, slide over to calc, 1 variable stats. List is our list 1. The frequency list for the probabilities that attach to these is list 2. And we get an average of 0.505. So you might say, well, wait a minute. He can't have a half of a win. Listen, it's an average in the long run. Think about this. If we were to do this scenario over and over and over again, most times there's going to be 0 wins. You're probably going to see 0 happen a lot. Every now and then you might get a 1 mixed in, and occasionally you might get a 2. But to be honest, 63% chance he wins 0 races, that's going to happen most often. So no wonder in the long run, the average is 0.505. I mean, think if LeBron James typically scored 0 points. Well, in the long run, his average is going to be very, very low. But again, because there are multiple outcomes, there is going to be a standard deviation attached to this as well. And the standard deviation was 0.721 wins. All right, so in the long run, if this horse were to race 2 races many, many, many times, the average number of wins would be 0.505, and the standard deviation would be 0.721 wins. Pretty simple. Hope everybody understands that. All right, one more problem. A magazine has 1,830,000 subscribers. Big magazine like Time or Newsweek, something like that. Now, of those subscribers, 980,000 are women and 850,000 are men. 35% of the women, oh, wait a minute, that sounds conditional. 35% of the women read the advertisements, okay? 45% of the men read the advertisements. Now, why does it matter who reads the advertisements? Well, if you're a marketer, if you work for a marketing company, you want to know who's reading those advertisements. All right, so here's the question. Imagine a random sample of 100 subscribers is selected. What is the expected number of subscribers in the sample who read the advertisements? Well, to find the expected number, we need a probability. So, because we need to multiply outcomes times probability, right? So we've got 100 subscribers. We need to figure out what percent of them, or what probability, or what proportion of them read the advertisements. So we have to kind of walk through this, because most kids will just say, oh, it's 35 for the women, 45 for the men, add those together. Whoa, 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 no, because those are conditional, right? We have to first have a woman to be that 35%, or we have to first have a man to get that 45% chance that they read the advertisements. So here's how we have to break this problem down. It's actually quite a bit of math, but none of it's very difficult. We first have to figure out what the probability is that we have a woman. Well, we were told that 980,000 were women, so divide that by the 1,830,000, that's 0.536. So 53.6% of subscribers are women. The men, I did the same thing. I got 46.4% of the men, or of the subscribers, are men. Then, remember, those were conditional probabilities. Of the women, 35% read a magazine. Of the men, read the advertisements. Of the men, 45% read the advertisements. Okay, so here's what I needed. I need to figure out what's the probability, what's the percent, what's the proportion that somebody reads the advertisements. Well, you could be a woman and you read, or you could be a man and you read. So I had to take the probability of being a woman, 0.536, multiply that by the conditional probability that if you are a woman, you have a 35% chance of reading the advertisements. So multiplying the 0.536 times 0.35, again, using my multiplication rules here. This is the probability of women. This is the probability of reading the ads, given that you're a woman. So I had to think the fact that 35% is only attached to the women. And that's how I got 0.1876. Then I did the same thing for the men. So I had to find the probability that you're a man and you read the advertisements. So first you have to be a man, which is 0.464. Then of those men, the conditional probability that of those men you read the advertisements is 0.45. Multiply that, we get 0.2088. So those are the two groups of people, women who read the ads and men who read the ads. So add those together because you can only be one. They're mutually exclusive. You can't be a woman and a man, right? So we're taking the women who read the ads plus the men who read the ads, add them together, we get 39.64%. So if we have 100 subscribers, that means we would expect 39.64% of them to read the ads. So 100 times 0.3964, pretty easy to do that math in your head, is 39.64 people. So remember, I want the decimal. I want the decimal because this is an expected value in the long run. If we were to look at 100 customers, 100 customers, 100 customers, 100 customers, 100 customers, 100 customers, over and over and over again, in the long run, we would expect 39.64 people to read the advertisements. Now, in any one trial, you're going to have a whole number. Wow, 72 people read the advertisements. Oh, 56 people read the advertisements. But in the long run, if we look at 100, 100, 100, 100, 100 over and over and over again, in the long run, we'd expect an average of 39.64 people to read the advertisements. All right, that's it for this video. Hope you guys enjoyed it. I know it was long, I know it was a lot, but it's a really good topic to explore.